Okay, everyone, let's get started here. I was just informed that the video from last week, I forgot to publish it, so I will publish the video. Some administrative things to take care of first. Talking to a couple of your classmates about exams and your grades. We are going to take our next to last exam. I'd like to do that next week on Wednesday. All right? So this would be exam 3. So exam 3 will be next Wednesday. All right, and then I'll give you some sort of review for this this Wednesday. That way you can work on it over the weekend, all right? I'm not saying we're going to spend Wednesday reviewing. I'm saying by Wednesday I should give you a review for the test. And then we can come back and talk about it on Monday, but at least you'll have it to look over for the weekend. Understood? That's the first thing. All right, second thing is that we're going to have a final exam. The final exam is on our schedule. I don't know exactly what day or time. I could look it up, but the final exam, what I'm going to do with this is this grade can replace your lowest exam score. So what I'll do is, let's say you get an 80 on this, and on another test you had a 72. You'll get an 80 for the final, and you'll get an 80 for the one that was a 72. All right, but the final is more of a comprehensive exam. It covers not every single thing we do like we've done, but it'll cover little bits and pieces from the entire semester. And it's a longer exam. Like our exams are 1 hour and 15 minutes, right in here, our normal class time. The final exam is 2 hours, 45 minutes. So it's a long exam, so I can cover more material on that exam. And that's why I'm saying, hey, if you can do that, then we'll replace your lowest test. Yes? Is everyone required to take the final? Normally, yes. I know what you're getting at, but yeah, I mean, they've told that the department has agreed to not do things like, oh, you don't have to take the final. Like, we've agreed as a department to not do that. Yeah, so not everybody follows it, but I kind of do. So if you have 100 average going into the final, it should just be, pretty straightforward for you then. So, okay, any questions on this? We're okay? Understand? All right, now, I sent out an email with homework, right, from the topic of last class, logarithms. Any questions on those homeworks? I was asking you to convert from one form to another. Y'all got that? Everyone got that email? Y'all are looking at me like...
Can we just go over one?
Yeah, which one?
Maybe just one of each. Maybe we'll do 4 to the power of x.
4 to the power of x equals 16. And then what's the other one?
Maybe a logarithmic form to exponential. So we'll just do log 2, 4 equals x.
Okay. So the main idea last class with this idea of a logarithm is that, this is something that we're used to seeing where there's no log involved at all, right? No logs involved. It's just 4 raised to some power is 16. And we could probably just look at this and get the answer, right? 4 squared is 16. But that's not what I was asking you to do on the homework. I wanted you to convert from this form to the logarithmic form. So we know it's going to become a log, right? Now, one thing you can always count on is when you're going from exponential to log, whatever number is the base here. In other words, whatever number is being raised to some power, That's your base. That will be the base of the log. So I can put that 4 right here. All right? And then the other side of the equation, this number, is what goes in the log. That goes here, 16. And then you put equals, and then you put the exponent here, x.
Oh, that's why I didn't do it. I didn't put the equals.
You didn't put the equals x. Okay. So that is this written in log form. Now, I also taught you about, or showed you this thing that I call the loop. And the loop is this thing we can use to check to see if we did it right. So you start with the base, and you say to yourself, if I raise that base to that power, does it equal that? So 4 raised to the x equals 16. That's what that should say, right? 4 raised to the x equals 16. And that's what we have here, right? So that checks out. So this is your answer, right here. Questions? All right, now this one is even easier than this one because you can actually just do the loop right here, right now. Just do the loop on this. So if I do that loop, that thing in red, I'm going to say, what? 2 raised to the x. 2 raised to the x equals, right, equals 4. That's the exponential form of that expression. That's it. That help? You're making it harder probably than it actually is. All right, so today what we'd like to do is we'd like to see if we can actually, did y'all bring your calculators? I asked you. I left mine on my desk. I told myself to bring it, I left it on my desk. Okay, so what I'd like for us to do here today is we're gonna need them in just a second. Trying to think of how I want to go about this. So, let's go ahead and define what a logarithmic function is. And before I put this up here, I'm just going to remind you that we've already studied what were called exponential functions. An exponential function, we did this. It was a function that looked like this. F of x equals a raised to the x. And we said that a had to be positive, and we said that a couldn't be 1. And we even graphed these. Looked like that if a was greater than 1, and it looked like this if a was less than 1 but still positive. Okay, right? We looked at these, exponential growth and exponential decay. So we know what these functions look like, 2 to the x, 3 to the x, blah, blah, blah. Now we're going to talk about logarithmic functions. In order to talk about logarithmic functions, you first had to know what a logarithm was. It's just another way of writing something, right? So here now I define for the first time what a logarithmic function is. It's f of x equals some log, and then the base of this log you put a, and then here you put x. That is the way we write a logarithmic function. And here a, again, is bigger than 0, and a can't be 1. So the number you put down here has to be a positive number, and it can't be 1, just like over here. And the reason that the restrictions are the same on a is because there's a very intimate relationship between these two functions. They are inverses of each other, right? And I told you before what an inverse does is it undoes what some function does. So if a function like doubles a number, the inverse would take half of that number. It would do the reverse operation. So that exponential function has an inverse, and this is what it is. So let's try and graph one of these. All right, we haven't done a specific example. Let's try and graph one. Okay, so I want us to, well, we'll do it right here. Example here. Let's sketch f of x equals log base 2 of x. I should probably have written down here what this is called. This is called the log base A function. And this right here was called the exponential base A function. The base is just the number down here, all right? So we have to be specific when we are talking about a logarithmic function what the base is. So the base here for us is 2, right? Now, do y'all remember how we graphed these? How did we graph these? It was the easiest out of all the graphing we've done. This was the easiest, right? What did we do? Table, right? And then we agreed to plug in -3, -2, -1, 1, 2, 3, right? That's the way we did that? We're going to do the same thing over here, but we're going to see it's going to be a little bit of an issue. So watch, and then maybe we can come up with a technique. I'd like to plug in some values of x and then see what the function spits out. Okay, don't write this down, all right? Don't write this down. I just want you to watch for a second. What would happen if I plugged in the number -3? Don't do this, right? Because you would think maybe I do -3, -2, do the same thing I did over there, right? Here's the problem with this. What is this asking me to do? It's saying log base 2, and then I replace the x with -3, right? All right, what is that? What does that mean? Well, convert that to exponential form. So this, do what you did on your homework. What would this turn into? 2 raised to some power is -3, right? That's kind of the exponential form of this. This is saying 2 to what power gives me this? Does anybody know what power you raise 2 to in order to get -3? You can't. You actually can't, but there's no way. We're not going to be able to think of it, right? It's not something our minds are going to be able to do. We're here, remember here when we made a table, all we did was just plug that number in. So if it was 2 to the x, we would just take 2 and raise it to the -3. That we could do on our calculators, you see? But this is a different sort of scenario. So the point is this. This is not efficient and it doesn't work well, all right? So the technique to graph a log is actually going to be something really weird the first time you see it. Ready? Here we go. So what we're going to do to graph this, we will use the fact that 2 to the x is the inverse. Right? So if I'm asking you to sketch log base 2 of x, right? Which means the inverse of this function is 2 raised to the x, right? This is an exponential function. This is a logarithmic function, but they are inverses of one another. So whatever this one does, that one undoes it. With me? So I'm going to make a table off of this. Off of this one, just like we did before. Here's x, here's 2 to the x. And we're going to do -2, -3, -2, -1, 0, 1, 2, 3. All right? Now, because we've done this several times, I'm just going to go real fast here. This is 1, this is 2, this is 4, this is 8. And then here we get 1/2, 1/4, 1/8. I trust that you could do that on your calculator, get decimals if you need to. Is that all right? So think about this. What does this function do to the number -3? Where does it send it? Over to 1/8, right? Where does it take the number -2? Over to 1/4, right? Takes the number -1, sends it to 1/2. Takes 0, sends it to 1. Think of it like a car wash, right? You put a car in, comes out the other side, right? It's a machine. That machine does the opposite, right? It takes every number here and takes it back to where it came from. So what I'm going to do is use this table to finish that table, to actually make that table over there. I'm going to say, okay, using this idea, I can figure out what the logarithm function does by just flipping these, just reversing the order of those. If I plug 1/8 in, I should get -3. If I plug in 1/4, I should get -2. If I plug in 1/2, I'm going to get -1. If I plug in 1, I'm going to get 0. If I plug in 2, I'm going to get 1. If I plug in 4, I'm going to get 2. If I plug in 8, I'm going to get 3. You get the idea? Everything is just reversed. Okay? And this is what I'm going to graph. Remembering that this right here, you look at that as a point. 1/8, -3. This is the x value and the y value. I'm going to go to a plot. I'm going to go to make a graph over here and put an x and a y axis. This is my x value, this is my y, and each one of these x, y, x, y, x, y, x, y, x, y. And let's take a look at what it looks like. So, all right, so let's do this first one. When x is 1/8, the y is -3. So let's let this is our x, this is our y. Let's let this be 1, 2, 3. When x is 1/8, 1/8 is just like to the right a little bit, right? Not very much, just to the right, go 1/8, and then you're supposed to go down 3. 1/8, down 3, I have a point right there. What's my next point? 1/4, -2. So move to the right 1/4 and go down 2. 1/4 is about, this is halfway, 1/4 is about right there. Go down 2, right there. The next point, sorry, wrong one. I don't want to look at this one right now. I want to look at this one. 1/2, go to the right 1/2, go down 1. And then when I plug in 1, it spits out 0. So go to the right 1 and then don't go up or down. And then where do I go next? 1 went to 0. 2 goes to 1. So I go, bless you, when I go to the right 2, I go up 1. Where's my next one? Go to the right 4 and go to 2, right? Oh, I'm going to have to go further out here. At 4, I'm at 2, up 2. What's my next x going to be? My last one. 8, that's pretty far out there, isn't it? So unfortunately, I didn't give myself enough room. But I get to erase, so I can just... 8's way out here, right? And up 3. Like that, roughly. And now I'm going to connect these together, all right? With a curve. What do you think happens over here? Yeah, it's going to do what a rational function did. Remember those vertical asymptotes we had? Same thing's going to happen. This is going to dive down, and this is a dotted line like that. And that is the graph of that logarithmic function. This keeps going like this. And it goes up. It keeps going up, but it's kind of slow. It goes slowly up. The further you go out, slower it goes. I mean, the further you go out, the higher it goes, but just very slow. That is the graph of the logarithmic function log base 2 of x. I want to show you something. Remember I erased this here? This right here was 2 to the x, right? 2 to the x. If I were to graph this, if I were to ask you to graph this, here's what it would look like. It would actually go here. At 1, you'd be at 2. At 2, you'd be at 4. And at 3, you'd be way up at 8. And then it's exponential growth, so it goes like this. And then it dives down like this, and you have an asymptote like that. That's what that one would look like. All right? So this is 2 to the x. And this one is log base 2 up base 2 of x. Those are two different functions, and that's what they look like. Do they look similar to you at all? Like, is it any sort of characteristics you see similar? Imagine you draw a diagonal line, perfect diagonal line, right through like this. This is the function y equals x. Tilt your head and look at it like that. And do you see that's a mirror image of itself? It's just a reflection over that line I just drew. All inverse functions look like that. When you draw one of them and draw the other one, draw that diagonal, it should be a mirror image over that diagonal line. All right? So, you get the idea? I mean, we're going to do another example. all right, just so you can see it from the start again. From the beginning. Let's do 3 to the x. Or sorry, not 3 to the x. Let's do log base 3 of x. All right, so next example, let's sketch f of x equals log base 3 of x. So what I'm going to do this, am I actually going to make a table for this? No, I'm going to make a table for what? 3 to the x, right? The exponential function, then whatever numbers I get, I'm going to flip them over, and that'll be the t-table for this one. All right? So we could, if we want to right now, make a t-table. We don't have to. X, this is log base 3 of x, right? But I'm not going to fill this table out until I first do this. I'm going to make a t-table for x 3 to the x. This one I should be able to do. -3, because I have a calculator, if need be. All right, so all we're doing is we're taking 3 and raising it to these powers. Let's see. 3 to the 0 is 1. I'm going to start there because that's always the easiest one. 3 to the 0 is 1. 3 to the first power is 3. 3 squared is 9, not 6. Be careful there, we're not multiplying, right? We're raising to a power. 3 to the third is 27. And then these you can get on your calculator, or you can just write them as fractions. Let's do the calculator. This first one should be 0.333 forever. What happens when you plug -2 in there? 3 to the -2. Somebody? Point. Is it 111? Yeah, it's 19.111 forever. And then the next one should be 1 over 27, so 0.0, what is it? 37, something like that. And it keeps going. We'll just round right there. Questions? So our table, right, for this function is actually just these flipped. So this is 0.037, -3. This is 0.111, -2. This is 0.33, ooh, -1. This is 1, 0. This is 3, gosh, I can't write today. 9, 2, and 27, 3. Yes? Oh, on the log, yeah, this side will always be -3, -2. Yeah, as long as you do it this way over here, then you'll always have, this side will always be that column. Is that a question? Yeah. Yeah. Hit times. As soon as it gives you the answer, just hit times and put in 1.0 and see what happens. Times 1.0, hit enter. Does it work? So what that does is it says, hey, I want to multiply this number by 1, which would be itself, but because you put 0.0, it knows that you want a decimal now. All right, so you ready? I'm going to go graph this. Now pay attention, because this is actually important in going to graph this. Do you remember when we were graphing this one right here? You knew that your x-axis would be between -3 and 3, right? Right? And then your y, your up and down, would be between these numbers, right? That's going to be reversed now, isn't it? Here, our y-axis, we're going to want to go as low as -3 down and as high as +3 up. So we want to be between -3 and 3 this way, right? And then our x values are going to go where? From here to 27. I need to be able to go out far enough to be at 27. So when I draw this, something like that, and maybe count by 5s. 5, 10, 15, 20, 25. Good enough. That should be good. And then my y-axis, I'm just going to go -1, -2, -3, 1, 2, 3, like Do you see how I'm doing that? I mean, like, because it's a logarithm and because we're using this method, this will always be between -3 and 3. Really, you have to determine how far to go out that way, and that's going to come off of this table, or this column right here. All right, let's try this first one. This is our x, this is our y. So 0.037 is a very small number, right? And I want to go down 3. 0.037, I mean, you can barely even put it on here. It's so small. And just come down 3 to -3. Put a dot there. 0.11 is just a little bit to the right, a little bit further than this one, right? To the right. So I'm just kind of estimating. See, does that point look like it's a little bit further to the right than this one? Just a little bit, right? Just a little bit that way. And then 0.33 over and down 1. So 0.33. Remember, this is 5, right? So 1 is like right here. So 0.33. We're estimating, okay? We don't have to get this perfect. Now at 1, I should be at 0. So if I make that a 1 right there, I should be right there at the x-axis. We already know this is going to do this, right? We already know it's going to do that, and there's going to be this vertical asymptote like that. And then as we go to the right, let's see, at 3 to the right, we go up 1. So 3 to the right, I don't know, somewhere around here, there's 3, and go up 1. And then you go 9 to the right, go up 2. Here's 9, go up 2. And then 27 to the right, way out here, and go up 3. And then once you have that, you can connect these together, and you have your logarithmic function. Now, I want you to be a little bit careful, because you remember when we were doing rational functions, we had vertical asymptotes and horizontal asymptotes, the magnet. This is not a magnet, okay? This keeps going up. There's no dotted line at the edge here, all right? Okay, that's it. Do you get the idea? To do a log base whatever, you first do, if this is log base a, right, of x, we first do a table for a to the x, get these answers, reverse them, plot those points, we're done. Now, I'd like to summarize, if I could. I'd like to do a summary. So, summary here of exponential and log functions. All right, if you have f of x equals a to the x, you have two different possible pictures that go with this. You either have this, that happens if a is bigger than 1. You have this. This is if a is less than 1. Do you remember what we called this? Exponential growth, and this is exponential decay, right? So exponential growth, exponential decay. Do you all see that these both have horizontal asymptotes? To the left it goes down, flattens out there. To the right this one goes down, right? That's what exponential functions look like. Now, we have this new thing, logarithms, logarithmic functions. Log base a of x, right? And we actually have two different scenarios here as well. The first scenario looks like this. This will happen if a is bigger than 1. And the other one I haven't shown you. If a is a fraction, I haven't shown this, but I'll just show you what the graph looks like. This is what happens if a is less than 1. So instead of coming to the left and going down forever, right? And then slowly growing this way, this one, as you go to the left, goes up forever, and then as you go up to the right, it comes down slowly like this. This would be called logarithmic growth, in logarithmic decay. Not that I would test you on that. I'm just telling you, all right? All right, so those are the pictures, all right? If you were to take these pictures and put them over there, here's what it would look like. This one would go like this, kind of, and then this one over here. This one's a little bit tricky. If I try and put that one over there, it would look like this, like that. And you can see that here, like I said, if you reflect, it's a reflection. And then do you all see right here? It's also a reflection. It's a little harder to see it, but it would be a reflection. If you take the blue and flip it over, you'll get the black one. All right, everyone good? All right, so let's see. When I was showing y'all exponential functions, we did like, I just told you that this could be any positive number, right? And do you remember I told you there were two special numbers to put here? Remember what they were?
Natural
The natural log, which means that the base was what?
was 2e.
E, that number, right? 2.718, you remember that? And then there was another one, 10, right? Because 10 fingers, you all remember this story? Yes? The two special bases. So over here we had the two special ones, right? Two special ones were f of x equals e to the x, and the other one was f of x equals 10 to the x. Those were our two special exponential functions, right? Well, if these are our special ones, I told you this one's because we live in a base 10 number system, and this one I told you has to do with calculus and slopes of lines and things like that. If these two are really, really important exponential functions, then don't you think their inverses are just as equally important to us? Yeah. So we have two special log functions as well. So the two special log functions are this. F of x equals log base e of x. And the other one is f of x equals log base 10 of x. See, it's the log base e of x is just the inverse of that one, right? And the log base 10 of x is inverse of 10 to the x. So these two are inverses, and these two are inverses, right? Now, historically, all right, historically, I'm talking about like when you look back at the history of humans and us becoming more intelligent, right? We started out by first coming up with a number system, then we started to develop math, right? And as we were evolving in our minds, our ability to compute things, in different areas of science, these functions were coming up. We were